Welcome to all of you to week 3. In this week, we will learn another new technique to design parameterized algorithms. And the technique which we will be learning this week is called iterative compression. Okay. So, the technique which we will learn in this week is called iterative compression. Okay. And the technique, as the name suggests, I think if I have to write a sentence or a line to explain the technique, I would just say that following. This is basically an incremental approach. It's basically an incremental approach. Okay. All these words will become clear as we go along in the lecture. So, what we do is that we build the instances up, build the instances up incrementally, and update the solution in each iteration. Okay. Okay. So, I think name wise we could have called it as it is called iterative compression, incremental algorithm, or we could have told inductive algorithms too, right? But let us look at this approach. What is called build the instances up incrementally. Okay, and so this paradigm is mostly suited for minimization problems. Okay. So, what are minimization problems? Basically, where you say, well, get solution of size at most k. Okay. For in our language, this is what minimization problems are. For example, vertex cover is a minimization problem. Odd cycle transversal is a minimization problem, right? Feedback vertex set is a minimization problem, and so on and so on and so forth. Okay? So, we will see lots of examples of this algorithm. Okay. So, first thing first up. Okay. So, I am going to illustrate this technique or some basic tools of this technique, illustrate this technique in this lecture on graph problems. Okay. So, the first word we learned, iterative or incrementally build the instances. So, instance to a graph problem is what? Instance to a graph problem is going to be, of course, graphs. say G, and of course, if there is a problem, we will have an integer k. But for now, let's not focus on this, but let's see how could we build the graph G incrementally or iteratively. Okay. Very simple. Assume that vertex set of G consists of following vertices V1 to Vn, n vertices. Okay. So, let us write down an arbitrary ordering of this. Okay. Arbitrary ordering of these vertices. Okay. What is this arbitrary ordering? Okay, I am going to write it for you. Okay. V1, V2, V3, Vn, Vi. Okay. And what is my graph? My graph is very simple. I am going to call this graph G1. I am going to call this graph G2. But what is G2? G2 is nothing but graph in. So, let us call the set Vi is like first I vertices in this ordering. So, what is Gi? Is nothing but graph induced on V1, Vi, V2, which basically means say capital V2. Okay. Let us just do small v1, small v3. Okay. These are vertices and these are sets. Okay. And what is G1? Graph induced on capital V1, which is just one vertices. So, of course, then we also have a notion of empty graph, because there is nothing, that is like G0. And what is this? It is Gi is what? Graph induced on Vi, right? And what is the last graph? It is Gn, which is same as G, right? Because this is induced on capital Vn, which includes every vertex. So, this is equal to same as G. Okay. Now, notice what is the difference between, let us try to understand what is a Gi and Gi plus 1. The difference is basically just one vertex Vi plus 1. So, basically what happens is that here is your Gi and you pick up another vertex Vi plus 1 and you just want to include Vi plus 1 into Gi. So, you just include. So, Gi plus 1 is nothing but Gi plus Vi plus 1. So, this is how we can incrementally build our graph. There was nothing specific about vertices. We could have also taken edges E1 to EM, M edges, and build our graph by adding one edge at a time. So, at Gi step you had to have a graph on I edges. In I plus 1 step you would have added a I plus 1th edge. So, this is how you can build your graph incrementally, right. So, and there is nothing specific about which ordering, no, just write down any particular ordering and this. So, now let us try to see what statements can be made. So, this is why this. So, what we are going to do to solve our favorite problem, say for example, let us say we have been talking about a vertex cover all the time, and we will again talk about vertex cover in a while, but just to illustrate this, let us take an example of feedback vertex set problem, which you have seen an algorithm in the last lecture or in the last week when we were doing branching. So, what is a feedback vertex set? Input is G comma K, okay. My parameter is K, and my question is, does G has a feedback vertex set F, okay. I will also denote F, of size at most k. And what is a feedback vertex set? Basically, G minus F is a forest, right? Okay. So, basically I want to delete minimum number of vertices such that what remains is a forest. And in the vertex cover, if you recall, what was the promise? That you want to delete minimum number of vertices such that what is left is an independent set. So, these are the graph classes where like these are the problems where we want to delete minimum number, delete some k vertices such that graph belongs to some family f. Okay. But beside that, let us just focus on one particular problem, which is feedback vertex set, that is we want to delete k vertices. Do you want to check whether there exist k vertices whose deletion gives me a forest? Okay. So, now I want to understand. So, let us see. Okay. Now, let us. So, I am going to solve my problem as follows. Solve the problem as follows, or rather let us say we are going to solve the problem incrementally or iteratively, whichever word you like, or inductively, whichever word you like. Okay. So, remember what is G1 comma k is like. So, we have, just to repeat this, given a graph G, we have fixed the an arbitrary ordering V1 to Vn, and Gi is nothing but graph induced on V1, V2, some first I vertices, which is nothing but capital Vi. Okay? That is it, just to once repeating is not bad. Okay? So, now I am just going to ask G1k. I ask myself, I am going to solve G1 comma k. So, like I have given this small little graph and k, and I ask, does there exist a feedback vertex set? So, this is so we are going to solve our main feedback vertex set problem. We are going to ask, we are going to solve different set of problems, like first we will solve one small problem, then another small problem, and finally by taking help from each of this, we will be able to solve the problem on the whole instance. Okay. So, now I ask some G1 comma k. Okay. There are two things, right? There could be two answers. Okay. One could say no, or it says, hey, look, here is your feedback vertex set of size at most k. Okay. Okay. So, I know that this small G1 comma k is a good for me. I can solve this. Then I said, fine. Okay. Then let me try G2 comma k. Right. Again, it can say no, or it can produce me a set S2, which is a vs of size at most k. Let us use the word letter f, because this is what we want to say, right? Okay. So, we keep on going asking this. Okay. Okay. But let us just look at first itself. Okay. What can I say if it says that G1 comma k is a no instance? If the moment I get G1 comma k as a no instance, we need not go further. Why? If G1 does not have feedback vertex set of size at most k, then G also does not have a feedback vertex set of size k, does not have, maybe I should write cleanly, does not have FVS of size at most k, then G also does not have FVS of size at most k, right. So, if a little graph, I can't delete k vertices, because what is feedback vertex set? Feedback vertex set is about deleting vertices so that you can hit all cycle, you can obstruct all cycle. If I can't, with k vertices, if I can't even obstruct cycles of an induced graph, because look at any solution, if you look at the intersection to that induced graph, that also forms a solution of size at most k. So, if I cannot even intersect all the cycles of a small graph, I cannot hope to obstruct cycles of the whole graph. So, notice, and there is nothing about G1 at any stage, at any stage if, right, I could replace this with Gi. So, at any stage, if we get a no instance, okay, if we get that, so at any point, if Gi comma k is a no instance, what will we do? Stop and declare that G comma k does not have G comma k is also a no instance. Okay. So, this is what we can, okay. So, this is one assertion, right. This is one assertion we can make, right. So, at any stage, so let us just for a moment that we succeed in each step, okay. So, let us, right. So, no, then we get F3 dot dot dot, right. So, at the last, either we get Fn or we get no, and what is this? So, Gn is equal to G, right, and Fn equal to F is your desired solution. Right? This is your desired solution. So, this is perfectly fine. So, now let us try to understand, let us cut this. Okay. Let us say looking again. You may ask what gain we get. Fine, I mean you are trying to solve your problem incrementally, like okay fine. So, rather than solving one problem, you have made n smaller problem and you are trying to solve. But ultimately that, I mean, yeah, what extra information did you get if you succeeded in each of this step, right? Well, let us see what happens. Okay, so we succeeded. So, now we are in the succeed branch. Okay, no nos. Okay, so now I am, let us see what we can feed. No nos, no nos, no nos. Okay, see what. Now notice okay. Now notice what happens. What is the property? So let's look at Fi. Okay, So this is, what is the property? So let's just focus on this part of the instance. Okay, what is the property of Fi? So property of Fi is, here is my Gi, suppose Gi, the property is Fi and G minus Fi is a forest. Great. Okay. Now, what is Gi plus 1? Gi plus 1 is Gi plus vertex Vi plus 1. So, notice if I push Vi plus 1 here, then F union Vi plus 1 is also a solution of size maybe at most k plus 1 of Gi plus 1, right? Because look, Fi, after I delete Fi, Gi minus Fi is a forest. So, if I look at Gi plus 1, with I not only delete Fi, I also delete Vi plus 1, then what is remaining? Gi minus Fi is nothing but Gi plus 1. So, in this graph, what is this? So, let us call it Gi minus Fi is same as Gi plus 1 minus Fi union Vi plus 1, right? And that is great. Okay. Let us call this set, I am going to call it set Fi plus 1 hat, okay, or I think hat might be a bit too much of a notation. Let us call this Si plus 1, okay. So, what is Si plus 1? Fi union Vi plus 1, okay, okay, or okay, or maybe, yeah, let us just leave that way, okay. So, we are getting an additional information. So, when I am trying, so what is a new instance? Look at what is the new information we are getting. The new information we are getting is the following problem. Okay. So, now if we are just specialize ourselves to a feedback vertex set, then let us ask ourselves what problem I am getting actually. So, I am getting the following problem, and as the name suggests, okay, we are going to call it compression FVS or feedback vertex set. What is the compression feedback vertex set? My input is G, K, right, and some S of size K plus 1 such that G minus S is a forest, right. So, you are also getting an additional information is that, okay, I not only give you input, I also give you a solution which is just one more, okay. My parameter is K, and my question is, does G has a FVS of size at most K, say F, okay. Now it will make sense to you why are we using the word compression, because what are we compressing? So, we have a solution of size K plus 1, and what is the question we are asking? Can we get one of size at most K, right? So, it is like, so which basically entails to us to say, can we compress? Yes, all right, that is it. So, this is why the word iterative compression, right. We are iteratively solving this problem, so that in every, so first of all we are solving iteratively, how? By building our instance or building the graph incrementally one vertex each, or you could do one edge each, or there are several other operations to build instances. You apply that, okay? And in each iteration, because it's a minimization problem, we will either be able to say, look, if I'm not able to find a solution to this problem for the smaller instances, then I will not be able to succeed in solving this problem for the general instances, okay? So no implies no for the whole problem, but if I have a yes, then I do have an extra information. And what is that extra information? That extra information is that I have a solution of size at most k to my current instance, which with the help of or the additional new vertex which is going to be added in the next instance gives me a solution for the new instance of just one size larger. Notice that if I would have just directly written, oh, input g comma s of size k plus 1 such and blah, you will ask me from where are you getting this solution? But the way this process is set up, this comes naturally. So it doesn't look like magic that, I mean, you are looking for a solution of size k, but you are given as an input a solution of size k plus 1. From where are we getting? But this is the beauty, or this is a strong point of this method, that this solution of size k plus 1 comes because of the inbuilt process which is involved in this whole method. Okay. So now, to solve FVS, what do we need to solve? Suppose if we can compress FVS in time, say g of k n to the power big O of 1, then we can solve feedback vertex set in time. How much? Look, we are going to call compress FVS how many times? N times at most. So, to solve FVS, need to call compress FVS n times. So, the running time is going to be n times g of k n to the power big of 1. So, for example, if, okay, which is still g of k n to the power big of 1. Okay. But this is cheating in some sense, because if this would have been n square, right, then this will become gk of n cube. But for the purposes of this discussion, let's just ignore it for now. Okay, it's just an additional factor in the polynomial, but you will see that sometimes it is important to get as good running time dependence even on the input side as possible, but let's not get into that discussion at this point of time. Okay, okay. Now let's look at compress FVS slightly more. Okay, okay. So let's look at compress FVS. Okay. Now, we have seen this kind of approach just even in our first lecture. I showed you how to do some of these things. Okay, but let's okay. So now let's look at how the world looks like. World looks like that I have S, I have G minus S, which is a forest. And what is my goal? Goal is to find f of size at most k. Okay. So now f could, how could f look like? F could look like, okay, picking some vertex from here and maybe picking some vertex from here, right? This is how could f look like. So let's call f intersection S, this part, y, which means yes, I will take you into my solution. That is why writing y. And this is S minus f, I am going to write n. Okay. So, now ask yourself, how many potential choices of f intersection S are? So, f intersection S could be, we do not know, could be any subset of size at most k of S. Okay. So, what I am going to do, for each potential y, okay, for each potential I, what problem are we solving for each potential? So, suppose if I have, so now if you notice, then the problem becomes as follows. What is left? This is what is left, which is n, right? And what are you looking for? You are looking for, and this is still forms a solution, right? But maybe of size k minus mod y plus 1. And now we are looking for f that is disjoint from no or n, right? Because we already have guessed y, right? So, you delete y. Like for most of the problems, we know that I am going to construct f which contains these y vertices, then I guess those vertices and I delete. So, what problem I am equating? So, in general, the problem which you will get to solve is the following. Okay. Okay. This is what is called disjoint compression problem. Disjoint compression FVS. Okay. These are generic steps. The feedback vertex set is just one example to illustrate, but you could try to do this for odd cycle transversal, vertex covered, any of the problems you have linked. Minimization problem. Input is graph G, K, S, okay, such that G minus S is for rest, mod S is at most k plus 1 or say k plus 1, parameter is k, and the question is, does G has a feedback vertex set of size f of size at most k such that, what is an important point, f intersection S is empty, right. So, we are looking for a feedback vertex set which is disjoint from the given feedback vertex set, and trust me, this additional property gives so much structure to exploit, and we will see several examples in coming lecture once I have set up the whole tool for you. But now imagine, okay, imagine now that if we could solve disjoint FVS, or for that matter disjoint compression FVS. Okay. People also omit the word compression if it is clear from the context, but let us, for our initial lecture, let us keep. If we could solve disjoint compression FVS in say alpha to the power k n to the power big of 1, or say some h of k n to the power big of 1, like where h k could be, where alpha is a constant here, let us say alpha is a constant. What can be solve our general problem? So, let us look at to disjoint compression FVS, right. So, I am going to tell you that now I will tell you how to solve compression FVS. Okay. So, what we do? Enumerate y subset of S of size at most k and solve disjoint compression FBS, right? So what is the running time of this algorithm? Running time of this algorithm is very simple. So I want to sum this up, right? I going from 0 to k, from k plus 1 choose I, right? So this is a size of S and this is a selection of Y, right? And then I am going to solve what problem? I am going to solve disjoint compression. Say for example, that runs in time alpha. So this is going to be alpha to the power k minus 1, k minus I n to the power big O of 1. So this is my running time to solve disjoint compression. But what is this? Let's see. This is upper bounded by summation. Let's get this n to the power big O of 1 out. I equal to 0 to k plus 1, k plus 1 choose I, alpha k plus 1 minus I, right? But then if you apply binomial coefficient, what is this? This is n to the power big O of 1, alpha plus 1 to the power k plus 1, which is like if alpha is a fixed constant, we can say this is nothing but n to the power big O of 1, alpha to the power k, alpha plus 1 to the power k, right? Okay, so then to solve FVS, right, what is this? N times n to the power big O of 1, alpha plus 1 to the power k, which is another alpha plus 1 to the power k. So this is why, so we will just concentrate on how to solve disjoint compression of a problem, because the moment we know how to solve disjoint compression, if we put up everything here, right, then you can get it. And similarly, I mean, if this not have been a sub fixed constant alpha, but like some function g of k, I mean, nothing would change. Like you can get some g of k plus 1 to the power k n to the power, like, yeah. Okay, maybe. Okay, just let's not try. Let me. I have not done the computation, but just check for yourself. Okay. So basically, what I'm saying that, yeah, some h of k. Okay, you can also do this, but like that's beside the point. Okay. So what I'm trying to tell you that like if we can solve disjoint compression problem, then we can solve the main problem. So what we learned, okay, so there's an outer layer, okay. What was an outer layer? Call compress in times, right? And that was because iterative building or incremental building of the instance, right? Okay. Now to solve compress, call roughly summation k plus 1 choose I going from k times a disjoint compress problem, right? So this is how we got up. So like, so let's just go back and let's see what we build. Okay. So now I think I have justified you the term or the approach, build the instances up incrementally, update the solution in each iteration. And why I use the word inductive, because you can think of these instances are built up inductively. We have built something of some size, then one extra, and so on and so forth. And so first I told you how to do incrementally build the instances example for the graph, which you will the most best test case, and then you will understand how to do other things. And I did it, I told you how to build for by arbitrary ordering of the vertices, but the same approach could also be done to edges. And then we looked at the feedback vertex set problem. We said what happens if we incrementally solve the problem. If at some point if we get a no instance, we can say no immediately. But what was interesting that when we are able to say yes, for the next instance we are able to build a solution of one extra size. So now we have an help, is that or we have a help that we do have a solution of size k plus 1, and your question becomes, can you find me one of size at most k with the help of this size k plus 1 size solution, right? And that led to, okay, from compress FBS to what we led to disjoint compress FBS. Now, look at what is additional property, because now we are not looking for a solution, but you are looking, you have reduced your problem to instances where you are looking for a solution which is disjoint from one solution. So, when you have this property, then what happens is that like you suddenly throw up so much more structure, because you are looking for two disjoint solution in some sense. One disjoint solution is given to you and you are looking. So, these structures are, these instances are way more structured, and one can exploit them to design algorithm, and that is what I will be doing in the next lectures. Okay, I will solve disjoint compress for several other problems. Okay, and that with that I will end this lecture today.